All right, so now we can carry on with Monte Carlo simulation. And I think today we'll look at some code as well as the theory behind it. So remember what we're doing here with Monte Carlo simulation. We are simulating the prices of assets, in particular here so that we can price options on those assets. And of course, I've mentioned this a few times. With Monte Carlo simulation, we have several advantages and disadvantages. Some of the great things about it are that we don't need a whole lot of market data to make it work. Um, it can be used for and virtually any option in the marketplace, especially the really complicated ones, which we often refer to as exotic options. In fact, it's particularly well suited for those types of options, but it can also be used for more standard ones like European call options. And it can also be used for many other applications as well. It's not just restricted to pricing financial assets. It can be used in a lot of disciplines like physics, for example. But here we're specifically focusing on the statistical properties of financial assets like stocks and bonds, interest rates, that type of thing. So that when we're done, at the end of the day, we can price a wide variety of assets that would not really be possible with more traditional methods like the binomial and trinomial option pricing models. It's not that you couldn't try. I mean, you can always try to price something with a technique. It's just that certain techniques are better suited for certain types of situations than others. So you would ideally like to use the most appropriate tools for each job, so to speak. So Monte Carlo is often saved for exotic options, especially when they are path dependent. Given that Monte Carlo is itself a series of paths, it makes sense that you would want to price path dependent options with it. So, but as you can see down here, there's other things we can do. We can use it for forecasting. We can estimate the Greeks. We can do a lot of other things as well. So, anyway, I did want to introduce briefly how we're going to go about our simulation. What we're basically doing here is choosing to simulate from the so-called uniform distribution and using that to generate the results that we need. Okay, so I'm pretty sure we started to go over this last time. Uniform distribution is a very simple type of distribution. In fact, we can illustrate it with a rectangle. And so let me just remind you what this looks like. So here's our uniform distribution. And it's formally defined, as you can see here. Actually, I just realized I've got purple here. Let's change that to black. So for the uniform distribution, we basically have a situation where all the numbers between a given upper and lower limit are equally likely to occur. Okay, so that's why we end up with a graph that looks like a rectangle. So whatever A and B are, all the numbers in between are equally likely to occur. Everything outside that range has no probability of occurring. In other words, the probability is zero outside the range A to B, but within the range, for any given value that we choose, its probability is the same as all the other values inside that interval. So a couple of consequences of this. First of all, since this rectangle is meant to be a probability distribution, or actually I should say, this is our probability density function. So it is written in two, it's written as a piecewise function. In other words, everywhere within that interval from A to B, we have a probability equal to the height of that rectangle, which is 1 over B minus A. Everywhere else, it's just 0. Okay. All right. So now the case we'll be looking at, though, with Monte Carlo is this one. You'll see why in a bit. Okay. We're going to look at only this one case where the probability distribution is defined between 0 and 1. Okay. So in other words, one over b minus a in this case equals 1, is just 1, actually. 1 over 1 minus 0. As long as x is between 0 and 1 and 0 elsewhere. And then the height is 1, the base is 1. So you can see it's actually a square. All right. It's technically, it's not a well, the square, of course, is a special case of a rectangle. So in this particular case, we have a unit square, as it's called. And so no matter what values I need, let's say I told you that some event is equally likely to occur over the next minute, let's say. So let's say here we have minutes. So to calculate the probability that x is less than or equal to 30 seconds, actually, what I should do here, if I want to be consistent, let me call that 0.5 for 0.5 minutes. And then you can see that in the graph, it's just that the left half of this rectangle. And so what we're doing is calculating the area, which is nothing but the base times the height. So in other words, there's a 50% chance that whatever this event is, it occurs within the next 30 seconds or half a minute. Okay, and so all of the probabilities that we need are taken from this, or calculated in this exact same way. So the reason why, well, again, you'll see why in a few minutes why we're using the standard uniform. So this one is not just uniform; it's not just any old uniform distribution. This is this so-called standard uniform distribution. And this is heavily used in simulation methods. What we're effectively doing is we're going to simulate from this standard uniform distribution and plug the result into another function, which will give us the probability that we actually want. In other words, imagine we're actually interested in not the standard uniform distribution, but the normal. There's a way we can take standard uniform random variables and plug them into a special function, which we'll see in a bit. And that will give us the normal random variables that we're actually looking for. Okay, so so this will always be our starting point. Now, if you go into Excel, you'll see that to simulate or randomly choose from this standard uniform distribution, it's a very simple matter of typing in the command rand. Okay, now it's kind of a bizarre function because we have no arguments going into this function. It's already understood that this is the standard uniform. The weird part, and I'm not sure why Excel set it up this way, is that every time I touch something on this spreadsheet, it's going to change that result. So if I try to do another one, for example, yeah, they're both different. So, so how do you get around that problem? You can just copy and paste these somewhere else. Paste special values will take care of that problem. You see, when I did that, these changed. So anyway, so the standard uniform has certain statistical properties that we should be aware of. We can calculate the moments in the following way. So for any uniform distribution, the moments are calculated as follows. meaning it's simply the average of the two endpoints. For the standard uniform, that would be, of course, 1 plus 0 over 2, which is a half. The variance, one-twelfth. And then the standard deviation, of course, is simply the square root of that. So if you take the square root, you're going to get approximately 0.2887. Okay. Now, what do we do with this information? Oh, by the way, Excel has other functions too. For random numbers. Like if you really need to directly generate random numbers from other distributions, what we're about to do isn't really necessary because what they have here is the data analysis toolpack. If you look at it carefully, you'll see that it does have a random number generator, which does offer you the option of really maybe not every single variable out there, but let's say I really do want to go directly, to the standard normal. I need 100 randomly chosen from the standard normal distribution. That would be the one with the mean of 0 and standard deviation of 1. I can just say, well, listen, please give me 100 random numbers from the standard normal distribution. And voila, there they are. Okay. Now, with only 100, I'm not sure how good this is going to turn out. I'm not sure if it's possible to graph this. Let me just see one thing here. I'm going to sort them. And I'm going to try to graph this and see if that. See, that's not what I'm. Although I must say, it's trying. Of course, if I have enough of these, I would expect to find a histogram that would, let's say, look like this. In other words, symmetrical about the mean. This is what your normal distribution is going to look like. So with only 100 random numbers, though, you can see it doesn't really. And plus, we'd probably ideally want to set up our own ranges of values, and we could do all that. We're not going to mess with it right now. But if we do this often enough, eventually you'll see that these do end up looking just like the standard normal distribution. So why are we not just using data analysis toolpack? Well, let's face it, many different programming languages don't have a data analysis toolpack. We need to have a method that works on all platforms, and whether it's Excel or Python or whatever the case may be. And so what we're about to do actually will do exactly that. All right, so here's where we're going with this. By the way, I just want to remind you about the existence of these higher order moments. For any probability distribution, we have 4 moments. And we're going to see, in this case, it's not going to be quite so important, but now I guess I shouldn't say there are 4. There are 4 that we commonly use in practice. These moments are measures of, think of them as summary measures of the properties of the distribution. So in other words, the first moment is expected value. And so we just saw how to calculate that for the uniform and the standard uniform. The second central moment, as it's called, is the variance. Okay. Now, just in general, expected value is written as expected value of X. And that the way we calculate it depends on the distribution itself. Okay. But the second central moment, though, is written in the following way. Oops. So in other words, you can see it's an expectation of the difference, square difference between X and the expected value of X. Now, in practice, this formula, what you're seeing there is true, but it's not easy to calculate. From that formula, this is how we normally calculate the variance. Okay, now, by the way, how do we get to these numbers? Well, let's say that we have a discrete distribution. Expected value comes from taking all the possible values of X and multiplying by their corresponding probabilities. If we have a continuous distribution, we're basically doing the same thing only with integration. So you're integrating over X, f of X, dx. Now, f of X corresponds to P of X. So in other words, this is often referred to as the probability density function. When we're looking at a discrete distribution, we often call P of X the probability mass function. You can see the equivalence between the two because, as you know, integration is just infinite summation. So on the left, we have a finite number of x's. On the right, we have an infinite number. And so that's how expected value is calculated. So the variance is taken directly from there. So how do you calculate, by the way, E of X squared? It's just a simple matter of replacing X with X squared here and over here. Again, the same thing. And then the E of X with the quantity squared is just, you take the expected value that you found up here on top and square the result. Okay, so now by the way, the standard deviation is not considered to be a separate moment. It is simply the square root of the variance. Then we get to this really interesting ones. The third standardized moment, it's called, is skewness. Now, unfortunately, skewness doesn't have its own like symbol that everybody agrees on. So here we're going to use this one, alpha 3. To recognize how this part looks a lot like the variance, doesn't it? Except that we're cubing the difference. Okay, right here. Right. So let's remind ourselves the variance over here, oh, whoops, sorry, that's squared. And so here we're going up to the third power, but you notice we're dividing by sigma cubed. This is why it's called standardized, by the way. Um, the reason why it's being done like this is to make sure the units fall within a convenient range. So the way this works is that essentially, for all practical purposes, um, if this is negative, means the distribution is negatively skewed. Which means basically it has a long left tail. Okay. In other words, something like this. Tell if it's negatively skewed because the mean is less than the median. And that's because there's several very large negative values in this distribution that cause the mean to be much smaller than it otherwise would be. Okay, so the mean is the most common, or the halfway point rather. The mean is the average. Now, if this parameter is positive, of course, everything works in reverse. The distribution is positively skewed. And so you end up with a situation like this. Okay, and that it can be demonstrated by showing that the mean is now greater than the median. So by the way, a good example of this in the real world is household incomes. Um, the thing about household incomes is that you often get situations where there's a lot of houses with similar values, and then there might be a handful of really expensive houses in the mix there too. And so what ends up happening is that the average is artificially increased above the median. So if you have a neighborhood with a lot of $500,000 houses and two or three mansions, you might find that the actual mean for this neighborhood is $2 million, but that's not very representative of the center of this data. So often in cases like that, we use the median instead of the mean to represent the center of our distribution. If you notice the government, when it reports on household incomes, they always report the median, not the mean. And that's the reason why. Okay, because the mean is a little bit deceiving, given that, you have a lot of houses that are close to each other in price, and then a handful of gigantic mansions pushing the average up, but distorting the results. Now, in the third case, we have symmetry. Or is said to be symmetrical about them. And this means we're looking at something that resembles the normal distribution. All right, so this graph isn't perfect, but you get the idea. It's supposed to be a mirror image on either side. So this is what a skewness parameter of 0 would look like. Although I must say, I mean, it doesn't have to be if you look at the uniform, you'll get the same thing. The mean, the left and the right hand side of the mean are mirror images of each other. So these both are symmetrical about them. Now, that's our third standardized moment. The fourth one is the so-called kurtosis. So we call this the fourth. And for all, I mean, in practice, there might be higher order moments, but we don't see them used very often. Even these two, you don't see that all. It's not a common thing to see these used, but for certain applications, these are very important numbers to look at. Okay, like in risk management, for example, this can help us see if there's any tail risk, meaning the risk of an unusually large loss to our portfolio over a given interval of time. This is how you would discover these things, by looking at the tails and seeing what's going on there. So the fourth central moment, and you can see, here it is. We'll just use alpha 4. You can see the resemblance right away, except that in the denominator, it's sigma to the 4th. So it's standardized by these sigma to the 4th. Now, this one is a little bit harder to explain and to visualize properly, but the way it works is this. The normal distribution has a kurtosis of 3. I know it seems like a little strange, but what we're going to compare it with, the other values of kurtosis tell us how much area there is in the tails compared to the normal distribution. So if this number is greater than 3, actually, I know what I'm going to do. Might as well take advantage of these. If I think I can copy this down below. Yeah, there we go. So just as a point of comparison, if the kurtosis is greater than 3, then you'll have what are called fat tails, which means more area in the tails, less in the center. Let me fix that. Not what I was hoping for. Let's try that again. All right, it's not awful. Like, okay. It's not great, but it's not awful. Okay. Now, what I was hoping you would see is that the red has more area in the tails, but not quite so much in the center. Okay. So in this case, we say that this distribution has fat tails, so that extreme outcomes, both positive and negative, are more likely than with the normal distribution. But then we have the other extreme. We've got less. Oh, let's try that again. Less than 3. Just means the opposite. So you're going to have skinny tails, they're called. Skinny, which means there's less in the tails and more in the center. Okay, well, I can live with that. You get the idea, I hope. So extreme outcomes are less likely than with the normal distribution. Now, in practice, with financial assets, the distributions of their rates of return, not their prices, but their rates of return, tend to exhibit fat tails. And you can kind of see why, because imagine that things are going terribly wrong in the economy. You can imagine a stock could have some pretty dreadful days, really lose a lot of money fairly quickly. But on the other hand, if things are going fantastic, you can see that they start to really bounce back and gain a lot. So, in other words, you tend to fluctuate between like very large losses and large gains, and then you have a lot of calm periods in between. But you tend to get very extreme outcomes with stocks and other types of assets. Now, here's an interesting twist. Um, Many researchers, well, I shouldn't say market, let's call them market participants, find that a scale of 3 for, um, or I guess I should say a standard of 3 is inconvenient to, let's say. So an equivalent measure was devised somewhere along the way. Now, I'll tell you why this is so important in a minute, but um, a closely related measure to kurtosis is something called excess kurtosis. This is simply kurtosis minus 3. Now, you might say, well, why did we bother with that? This has the convenient benefit that if excess kurtosis is 0, then the distribution matches the normal, or it has the same tails as the normal distribution. Excess kurtosis, which is negative, indicates skinny tails, and an excess kurtosis that is positive indicates fat tails. It's just a matter of being comfortable with the units. Okay, so there's regular kurtosis, the way it's formally defined. 3 means the same as, same layout, the same tails as the normal distribution. Below 3 means skinny tails. Above 3 means fat tails. By calling it excess kurtosis, by simply subtracting 3, it's easier to visualize that 0 means the same as the normal, negative is skinny tails, and then greater than 3, positive is fat tails. Turns out, though, that there are other convenient properties that excess kurtosis has too, although I'd have to look up some of these, but I read that it's not just like for academic reasons, like, well, 0 sounds nicer than 3. There are some actual benefits to using excess kurtosis. But let me just quickly sketch these in again. So red we used before for fat tails. And then we use purple for skinny tails. All right, now we can see them all side by side. All right, now, what I'm going to show you is something very interesting here. If we go into Excel, let's say we have some data or other, it doesn't matter what it is. Let's say I've got a bunch of returns, like these returns. Oh, actually, no, I see what I did. I sorted them already. Um, let's just say I have this stock. Actually, these do the job. These are taken from the normal distribution. But no, let's pick a different one because this is the standard normal. What I'd like you to see is let's say we have a stock that has we assume stock returns are norm. And let's assume though that instead of standard normal, it has a mean return of 0.08 per year and a standard deviation of 0.20. Okay, so what I'm going to do is get into the bottom and calculate these moments. Actually, it doesn't, Excel doesn't have, I just realized this one we have to do ourselves if we want to calculate the expected value of the variance. So I'll tell you what, let's just focus our attention on skewness and kurtosis. How about that? So the Excel command for skewness is skew. So it's, wow, it's a fairly, the skewness is fairly large, which indicates this case. Okay. But it's the kurtosis that I'm really interested in. So we type Kurt. Back with 1.7. So here's what I'm going to do. See if I'm going to see if I can come up with a graph here. Oh, this worked out beautifully. Oh, I'm so glad this happened. Now you can see the positive skewness. I don't know if you can really see the kurtosis properly though, but you can definitely see the skewness. Remember, skewness of 0 would mean perfect symmetry. So here we've got clearly a very much positively skewed distribution. But the kurtosis, I'm not sure how, if we can truly visualize it, but well, anyway, what I'm building up to is this. Surprisingly enough, when you go into Excel and type in the kurtosis and the Kurt, it turns out that those guys at Excel who invented it also liked excess kurtosis better than kurtosis. So Excel's version of kurtosis is actually excess kurtosis. They don't tell you that. So we end up using this in VBA. We have to keep an eye on that. The kurtosis command in Excel is actually giving us excess kurtosis. Now, in my opinion, that's a mistake. If they're going to call it that, I mean, if they're going to do that, they should call it excess or something to warn you that this is actually excess kurtosis that you're seeing here. And that means it's positive, and that means we should expect to see really fat tails. I guess you could make the case that it has fat tails. It's hard to tell. It's not the best example, but the skewness is very clear. Okay, so I thought I'd change it to red. So yes, that 1.7 means compared to 0, not compared to 3. Otherwise, it would have skinny tails if this was regular kurtosis. If you go into their instruction files, or we could go to Google, I suppose. Yeah, see, it says here negative kurtosis means relatively flat, meaning skinny tails. Anyway, so we'll get back to that later on. Okay, so now we're more comfortable with these moments. These moments will be proved to be very important in Monte Carlo simulation because sometimes we can tell if our simulation is working well by looking at not just the mean and the variance or expected value and variance, but also the skewness and kurtosis. All right. Anyway, now here we're going to build up and finally show you at long last why the standard uniform distribution is so useful for simulation. So if you remember, let's get back to this document. The normal distribution can be characterized in two different ways. And that what you're seeing there is actually the function going on behind the scenes of the normal curve, the bell-shaped curve. And this is going to tell me the probability that, let's say X is normal. A mean of mu. Hold on, I have to, there, hold on, there we go. Um, I was just adjusting my phone for a second there. So the probability of it being less than or equal to some constant lowercase x which you see in the graph here, would actually be obtained by doing this. Okay, so you're integrating from negative infinity up to this lowercase x. And remember, this f of x is what we mean by the probability density function distribution. But guess what? We also have an equivalent function which looks like this. What is going on here? What is this capital F thing here? This is called the cumulative distribution function of the normal distribution. And it lets us calculate directly what are called cumulative probabilities. So in other words, if I wanted to know, let's say that I choose sex to be 1, that gives us a probability of approximately 0.8413. And so if I want to find the same thing here, what will happen is this curve is showing me less than or equal to probabilities. Okay, so you notice how it's accumulating as I move to the right. The area is getting larger and larger, although it can't go above 1. This is the upper limit because this, what you're seeing here, these are probabilities on this vertical axis. Okay, so it can't go above 1. That's an asymptote for this function. But I can solve directly for this case. That's interpreted to mean that the probability that x is less than or equal to 1 is 0.8413. Okay, now I'm not sure if Excel has this built into it. Um, that's got to be there. Hold on. Oh, that's right. I remember now. Yes, yes, yes. See, here's what they've done. In Excel, they have a function called norm.dist, where the first value is the number you're looking for. But then they have a parameter here. Aha. So, in fact, we could experiment with this a little bit. I wasn't sure. I had to remind myself because in I teach statistics a lot, and you don't often see, at least not the level I'm teaching at, the CDF. It's usually always, well, everything is done in terms of, I should say, cumulative probabilities. Okay, so equals norm dist. X is the 1. Oh, actually, I'm sorry. You know what? When you're using the standard normal, which is what we're doing here, it becomes norm. Let me just change this. You need that little S in there to remind it that this is standard normal. And that in turn means that the mean is 0 and the standard deviation is 1. It's a special case of the normal distribution where the mean is 0, standard deviation is 1. This is the one we use most often. Okay, so all right, let's go back here and try that again. Norm.s.dist 1, 1. Okay, so what this is saying to me, well, you see, it's just disobeying me right there. We can think of this in two equivalent ways. Okay, so in other words, any way you slice it, where the area is or probability is 0.8413. This one is showing us areas below a certain point. This one is showing the heights of the curve. Okay, so this would be f of x here, lowercase. This is the capital F of x. Okay, so if I type, oh, wait a minute. Oh, I spelled it wrong. Sorry. So basically, this function is what I did here. So how do you interpret that number? Now, this is equal to the height of this curve. Now, this is the kind of thing we don't actually need for what we're about to do. Okay, so all we care about is the probability, which can be interpreted as either the area below a point under the um, probability density function or the height of the curve, the so-called CDF. Okay, now this is where it gets interesting. The CDF can be inverted. And how do you know this, by the way? Because just by looking at the graph, you can see this capital F of x is a one-to-one function, which means that for each x, there is a unique y, and for each y, there is a unique x. So a good analogy in the real world would be like people and social security numbers. You know, each person has one social security number. No two people can have the same social security number. So that's a one-to-one relationship. And why does that matter? Um, oh, one more thing. I just want to mention that graphically, it can be seen that this is a one-to-one function because it passes the the horizontal line test. What does that mean? Well, if a horizontal line is drawn through this function, it will only cross the function once, and where I put it. And so why is this important? Because all one-to-one functions are guaranteed to have an inverse. So in other words, just by looking at this thing, you can tell. So in other words, the one-to-one, sorry, the horizontal line test means no matter where I put a line, it'll never cross more than once. So F can be inverted. And so how would that work? So yeah, so in other words, F of 1 equals 0.8413, meaning okay. So you can turn this around by saying that I guess that's how I'm trying. It's hard to explain this in English sometimes, but in a way, this is like, you might recall from your travels, the arc sine function. If you know that, for example, the sine of, let's say, I'm going to double check here. Let's say you're told that the sine of 60. Oh, no, let's try 30. You might recall the arc sine function simply reverses this. Okay, so now, so you can see it's a similar idea to the arc sine function. It's an inverse. And so they're taking you two different directions. Now, again, what does this have to do with anything? So we're going to tie these together right now with a graph in the slides, I believe. So yeah, so this is one. Oh no, this is a slightly different example. So imagine that we did the following. Here's my graph. We know that f of 1 is 8413, meaning the probability that x is less or equal to 1 is 8413. This implies that f inverse of 8413 is 1. So in the first case, I've got a 1 and I'm associated with 8413. I have an x of 1, I reverse it, and it becomes 8413. This one is telling me that given a probability of 8413, what value of x does this represent? And that would be the 1. So here's what we're going to do with our Monte Carlo simulation. I'm going to try to draw this properly. Imagine I randomly simulate from the standard uniform, and I come up with 0.8413. If I feed this into this f inverse function, I end up with 1, which is taken from the normal distribution. So what I've basically done is I've converted a standard uniform random number has been transformed into a standard normal random number by randomly simulating from a standard normal distribution, standard uniform distribution, and substituting it into the inverse CDF function. F minus 1 for the standard distribution. So it's like, again, if I could draw a little graph here. Here we go. Difference between the two is that this is the probability density function. This is the inverse CDF. Now, how would you carry that out in practice? Well, to simulate from the command to choose a random number from standard uniform, as we already saw, is rand. The Excel command, or the inverse CDF of the standard normal distribution, is norm.s.inv. Okay. So in other words, the command will be something like that, equals norms.inv. Here it is. And so this would do what you see up here. And this, because it's Excel, this can be used in VBA to generate all the standard normal random variables that we for a Monte Carlo simulation, I mean. Because the model that we'll be using, the Black-Scholes model, is going to require normal random numbers. Now, once, of course, we have to say this for next time, but once we do this, you'll see it's very straightforward. It's very simple. It's just time consuming. And so with that in mind, now here, by the way, just as a side note, this inverse CDF function, if I have an inverse CDF function for the T distribution, I can use the same approach to simulate from the T distribution, or of the inverse F distribution, I can do the same thing. So you can see why this approach is very general. It works under a lot of circumstances, as opposed to trying to create a CDF directly. It's much easier to do it this way. And so again, all we need is an inverse CDF function and we're all set. And so this is why we typically use this approach, because Excel has quite a few of them and many other programming languages do the same. So that's going to be the heart and soul of our simulation process. Okay, so now, by the way, when we get to the code, you're going to see it's almost laughably simple because, Excel is really doing all this work for us behind the scenes. But at least now you'll understand what in the world are we doing? Okay, how can we justify what we're doing? And then when we run these simulations, you'll see how many trials it takes to get within a certain amount of accuracy of whatever it is we're aiming for. So we typically test it on the Black-Scholes model to see how many paths are necessary to get within a certain amount of the true price. Anyway, so this is it's been quite a statistics lesson. So I'll be posting these right here along with the video. And then the next time we meet, which I'm hoping will be this weekend, maybe Sunday, we'll actually look at the code and see how this is being implemented. And then I'm going to actually find, for the first time, I'm going to give you an assignment because I think this is a great way to get some practice with VBA, and because it's very flexible and you can do all kinds of things with it. So you get to write your own code, but first I have to show you how this is structured in VBA. So Anyway, so we have a lot to look forward to, so I'll see you soon. All right, good night.